So today we talk about the next topic in our discussion, which is on crystal system and lattices. In our last class, we have referred to a few topics. The topics which we referred to in our last class was that what is the concept of lattice as such, and we said that we explained it with the help of a two-dimensional lattice. Then with respect to the concept of lattice, we explained what is the concept of unit cell, and in this unit cell we said you can have what we call as primitive unit cells and as well as the non-primitive unit cells. We have discussed that what is the difference between these two terms, whether you can call it as a primitive or a non-primitive one, and other topics which we referred to lastly were related to these two issues only. Now we move forward regarding our discussion on two-dimensional lattices, and then we go on to the three-dimensional lattices, and we will introduce today the concept of Bravais lattices, that is why there are only 14 lattices which are possible. Just to begin our discussion, we can just say that if you remember the description of lattice, we defined lattice as an arrangement of points such that each point has identical surroundings. Another thing which we refer to that this lattice must be what we call as space filling, and if you remember, we also introduced the concept of motif or basis there. We have said that based upon this discussion we were able to devise that what is the difference between the term lattice or crystal lattice. We said lattice is just nothing but an arrangement of points, and what is there at these points is given by the motif. So at these points, which are known as lattice points, there can be an atom or a group of atoms, and that is how we said that how we say that lattice plus motif is going to give us what we call as the crystal lattice. Let's move forward from this, and then we see that how you can classify crystal lattices, and then we go to the 2D lattices first, and then we go to the three-dimensional lattices in our next discussion. Okay, coming to the two-dimensional lattice, we say there are only 5 possible arrangements in 2 dimensions which are unique, because we want to have unique arrangement of points. So right now I'm only referring to lattice, so all of them are just points. So when I talk about these 5 possible arrangement of points which are unique to each other, we say the first one here happens to be what is known as your oblique lattice. The second one is referred to here as square lattice. The third one is here referred to as hexagonal lattice. The fourth one here is referred to as rectangular lattice. To be specific, we call it as rectangular P, rectangular primitive. and the last one here happens to be again a rectangular lattice, which is rectangular, which is centered. Okay. Now, when I refer to these 5 different distinct arrangement of points here, the first one we say is the oblique lattice. In this particular case, the conditions are that the vector A is not equal to B and angle phi need not to be equal to 90 degrees. It is not equal to 90 degrees. In a square one, we say the vector A equal to B and angle phi equal to 90 degrees. The hexagonal one, we say that A equal to B and phi here happens to be 60 degrees. In a rectangular one, we say A not equal to B and phi equal to 90 degrees. If you look at this first one, which we have been saying as oblique lattice, and this is the generic one, and the second one, the square one and the hexagonal one, these are the specific types of oblique lattice, means these are special cases of oblique lattice. When A is equal to B and phi equal to 90 degree, oblique lattice is known as the square lattice. And when the second case, when A is equal to B and phi is equal to 60 degrees, oblique lattice is called as the hexagonal lattice. So the second one and the third one are the special case for the first one, which is available to us here. And then we have the rectangular P, that is a rectangular primitive, and then we have the rectangular C, where conditions are A is not equal to B and phi is not equal to 90 degrees. Keep it in mind that in this particular one, the lattice is given by these two vectors. So we will see it today only, that what is the meaning of these terms here. Okay, so this is the 5 possible arrangement of points in 2 dimensionals which are unique and which are possible as such. Means there is nothing except these 5 arrangements which can be unique. Whatever arrangement of points can be there in a plane, it can be described by any of these 5 lattices known as oblique, square, hexagonal, rectangular P and rectangular C. Okay. So now coming to the description of the unit cell that we referred lastly, we say if this happens to be a primitive unit cell, the lattice points are only at the corner. So you have the lattice points only at the corners here. There are no lattice points except anywhere in the corners. And if it is a P unit cell, we also know that it just have total 1 lattice point. It is just 1 lattice point here. All of them, because there are 8 corners, so they are shared, so only 1/8 comes from each edge here, each corner here, and that is why the total lattice points contained in this primitive unit cell happens to be 1 only. And this is 1 unit cell, so when you stack these unit cell in a particular sequence, you create what we refer to as the crystal structure. It will be a crystal structure if these points are occupied by atoms. So we are saying now these black ones are atoms. So if these points are occupied by, let us say, a single atom only, then it becomes a crystal lattice. And then when you replicate this unit cell in 3 dimensions, it gives you what we refer to as a crystal structure. Okay. Now, in our discussion about crystal structure, we also will be referring to one thing called as crystal system. Now, referring to a crystal system, and that is now we are referring to it in 3 dimensions here. we understand here that there are actually 7 crystal systems which are possible. There are total 7 crystal systems, and their conventional unit cells is what we are trying to show here. The first one happens to be the cubic one. So if this is the first one, here is the conventional unit cell for a cubic crystal system, where we find that it's A equal to B equal to C. The 3 vectors are equal, that is the edge lengths of the cube are same, and alpha equal to beta equal to gamma is equal to 90 degrees. So this is the first one. The second crystal system, which we say is tetragonal, where A equal to B but not equal to C. So this is the second one which we are trying to show here, is the tetragonal one, where A is equal to B not equal to C. The angles are still 90 degrees. The third one happens to be an orthorhombic one, where we say, this is the third one, where none of the edge lengths are equal, that is A not equal to B not equal to C. They but the angles are still 90 degrees. So alpha equal to beta equal to gamma is still 90 degrees. So this is the orthorhombic one. Then we have the hexagonal one. Now keep it in mind that we are calling it an hexagonal crystal system, and it does, if you have studied chemistry, solid state chemistry, you may have heard something known as HCP, hexagonal closed pack systems. So this is not HCP. We are referring to it as just an hexagonal system. So we have the fourth one here, crystal system, which we say is the hexagonal crystal system. What is there in this case? That A equal to B. So this is A equal to B not equal to C. So the two vectors are same. In this direction, the vector is not equal to A and B. And the angle here happens to be 120 degrees. So if we are looking at it, it becomes somewhat as a parallelepiped. So if you are talking about this hexagonal system, if you draw the conventional unit cell of it, it will look something like this. So this is the fourth one. Then going forward, we have the fifth one, which we call as the trigonal, where this is the fifth one here now for us, where we say that A equal to B equal to C, the edge lengths are equal, but the angles are not equal to 90 degrees. Angles are equal but not equal to 90 degrees. That is alpha is equal to beta equal to gamma not equal to 90 degrees. So this is the next one. Then I have the monoclinic one, where we find that the edge lengths are not equal, that is A is not equal to B is not equal to C. The angles alpha and gamma are 90 degrees, and beta is not equal to 90 degrees. So we have the third one, this one here, sixth one here, which we say is the monoclinic crystal system. Then I have the triclinic system, which we say is this one, the last one in our discussion here, 7, which we say is the edge lengths are also not equal, the angles are also not equal. In a way, we have seen that these are the several crystal systems which we are referring to in our discussion here, 5, 6, 7. We have described them in terms of their conventional unit cell. Conventional unit cell. That is, how does their conventional unit cell look like? And if you look at all these unit cells carefully, whether this is the one or whether 1, 2, 3, 4 or the other ones, all the unit cells that we have referred to here are p-type unit cells. Means they are all primitive unit cells. Means they have the atoms contained only at the corners. So they are all p-type of unit cells. We say are the primitive unit cells. Another thing that you can see here very easily here is that there is one term called as symmetry. We will talk about its symmetry in our discussion on crystallography later also, but in terms of symmetry here, if you look at this table here, we can say here that when you move down this table, the symmetry is decreasing. Symmetry is decreasing. Here, cubic one is the most symmetric crystal system, where the edges are all equal, the angles are also equal. So it's the most symmetric one. Then you lose some symmetry here, then you move going forward, going down this table, we find the symmetry is decreasing. So it's a good observation, which we'll try to later on see that what is the significance of this observation, that how does it help us in understanding the concept of symmetry here. So we will come back to the concept of symmetry later on, but for the time being we move ahead. So these are the several crystal systems which are possible. Okay. Now, if I consider this unit cell here, which I say is a P type of unit cell, which is a primitive unit cell, for the time being we are saying that if A is equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees, then which type of crystal system this belongs to? This unit cell then belongs to a cubic crystal system, a cubic one. But this is a primitive unit cell, means the atoms are only located at the corners and there is complete one atom in this unit cell. So the smallest unit cell also possible, which is another definition of the primitive unit cell. But this does not take care of our some of the known crystal structures, which we are known as FCC or BCC. So it doesn't take care of that. This is what we refer to as a primitive one, or also referred to as simple cubic. So this is basically a simple cubic. This is a simple cubic unit cell, or a simple cubic crystal structure. Okay. Now, in this primitive unit cell, there are other possibilities also. Means in a primitive unit cell, the lattice points are only at the corners. That's what we are seeing here. There are other possibilities here. So the first one, which I say, is the primitive unit cell, where the lattice points are only at the corners. So don't mind about this 7 here. It will be discussed later on, just after this slide, that what is the meaning of this. There's another possibility that a unit cell can be I type, which is body centered one. So in addition to the atoms at the corner, you have one atom at the center here. We say this is I type unit cell, where we say it is what we call as a body centered one also. There is another possibility that there can be a face centered unit cell. Means that now, in addition to atoms which are there at the corners, we have atoms at all the faces now. So in the body centered one, in I1 you had at the center of the body, but in a face centered one we say that now they are at the center of all the faces here. So there are 6 faces of this cube, and we find that you have the atom or the lattice points now located at all the faces. So we have the lattice points not only at the corners, so you have the lattice points at the corners, as well as you have the lattice points at all the faces, at the center of all the faces. So at the center of all the faces you have the second lattice point. So we call that as face centered one. And then we have another possibility, which we say is end centered. Means now in we don't have the lattice points on all the faces of the cube here, but we have only on 2 opposite faces. So you can have on the 2 opposite faces, one here and another one here. So then it becomes end centered one. So corners plus 1 pair of parallel faces here. We have said that these are the four possibilities, which is P primitive, I is body centered, F is face centered, and C is end centered. These are the four possibilities which can happen in any crystal system. We have shown only in the case of a cubic crystal system. So you have 7 possible crystal systems with us, and in those 7 crystal systems it is possible to have, in each one it is possible to have these 4 variations of the lattice. That is, it can be primitive lattice, it can be I lattice, it can be F lattice, and it can be a C lattice. And going by this, you can have 7 into 4, 28 lattices which are possible. So there are 28 lattices which are possible. But if you recall what you already know, most of you, that we have only 14. We have only 14 Bravais lattices. We have only 14 lattices in place of these 28. So 28 may be possible, but we have only 14. So why it is so? We will answer this also. That there are reasons that why you cannot have 28. Okay. So this is just to add on to this now. So I am now saying that you have 7 crystal systems listed here. These are the 4 various types of lattices: the primitive one, the body centered, the face centered, and the end centered. And as such, when we said that you can have 28, but you only have these 14. So now you can understand what is the meaning of these 7 here. That all the 7 crystal systems, they will essentially have the primitive lattice. All the 7 crystal systems, cubic, tetragonal, orthorhombic, hexagonal, or any one, all of them have the primitive lattice. All of them have that. So you have these 7 lattices, which are out of the 14. You have 7 available here. So you have 7 here. Then out of these 7 crystal systems, just 3 of them have the body centered one. That is, I lattice is only available in these 3 crystal systems: the cubic, the tetragonal, and orthorhombic. Then coming to F, we have only 2 crystal systems which have face centered lattice available with us. That is, you have the cubic FCC, which is nothing but FCC. This is nothing but BCC, that is body centered cubic, face centered cubic. And you have the orthorhombic, which also has this face centered lattice available to us. So you have 2 here, and then further you have 2 more lattice available to us here, which are C type, available in orthorhombic and in monoclinic. So you have these 2 available to us in orthorhombic and monoclinic here. But what I see is that there are number of, so you could have possibly 7 into 4, 28 types of Bravais lattices, but we have only 14. So there are many vacancies. So you don't have this here, you don't have this here, you don't have this here. So many vacant spaces are there. Now we will try to answer that why these spaces are vacant. Some of them are vacant because we wanted to have for unique arrangement of points or unique arrangement of atoms. So when I say I want to have unique arrangement, it is proved that there can be only 14 unique arrangements. It means the other arrangements may not be unique. Means this can be represented by something else, and that is why we do not have the end-centered cubic lattice. So, and we will prove it later on that why it is so. So this is as far as the discussion on the type of lattices and the 14 Bravais lattices is concerned. Thank you.